Hello everyone, I am Felix Limanta from Tokyo Institute of Technology, Japan, and I will be presenting my paper titled Camera Angle Aware Multi-Object Tracking. First is the introduction and previous works driving this research. So MOT, or multi-object tracking, has several outstanding challenges that remain. One of them is occlusion, which causes detection failures and tracking failures. Another is the difficulty of measuring the distance of objects if they are aligned in the depth direction. These two problems cause identity switches, among other problems. So knowing the object depths can address these challenges, or at least start to overcome them. One previous work by Corona in 2020 plugged in an off-the-shelf monocular depth estimator for MOT. This somewhat solves the occlusion problem as the objects are modeled in 3D, but the imprecise distance problem still remains to be solved. Also, the depth estimator may also incur significant computational costs. To overcome occlusion in MOT, the most common method is to use re-identification or re-ID to link detections before and after occlusion. However, re-ID cannot reliably handle longer occlusions due to a drift in the visual features the longer the occlusion is. Another method is to lift the tracking from 2D to 3D using monocular depth estimation, stereo camera, existing LiDAR point cloud, or others. MOT in 3D can itself be divided into two. The more commonly known 3D detection or tracking does all processing in 3D, from the input-output bounding boxes to the internal processing. Another is to add 3D reasoning to 2D MOT. Here, the input-output bounding boxes remain in 2D, but uses 3D for internal processing and track management. For example, Corona applied a monocular depth estimator to generate a depth map and augment the sort algorithm. Quo Vadis transforms a scene into a bird's eye view, then applies trajectory prediction to tracks. Both of them are relatively computationally expensive, especially with more and more added components. Next, about camera pose estimation, traditional methods such as RANSAC or PNP requires handcrafted features, while deep learning methods work out of the box with as little as a single image. However, most methods require a dynamic moving video and/or a well-defined structure, both of which are rarely available in MOT cases. Therefore, we propose CAMOT, a simple camera angle estimator for MOT. Assuming multiple objects with uniform height are located on a flat plane, we can estimate the camera angle using bounding boxes obtained from object detection. The scale of each individual bounding boxes informs us of the object depth, while the bounding box distribution on the image informs us of the camera angle. Our method is simple, as it only uses object detection results. Next, we'd like to talk about the details of our method. So the key idea here is simple. If we assume a known uniform object height h and a known theta, we can calculate everything else from the object depths or the 3D coordinates. However, since we don't know the actual theta value, we need to iteratively estimate theta until we get the best value for that frame. So, we assume an initial theta value, then estimate the 3D points using theta. We use the estimated 3D points to regress a common plane, then use that plane to get the estimation error for theta. We repeat this until the estimation error is minimum. Our scenario is currently a crowd of humans in a public space, which is common in MOT datasets. We make the following four assumptions. 1. Unknown camera parameters except for the focal length f. 2. At least 3 objects detected in the frame. 3. Objects are in contact with the ground. And 4. Camera angles change smoothly over time. We formulate the problem as finding the optimal angle, minimizing the error for the best fit plane between all objects. We use the pinhole camera model, and we model objects as cylinders with uniform height. To estimate depth with detection results, we use the camera angle to find the distance from the origin point to the object top and bottom points. We first convert 2D pixel coordinates into 3D rays. Afterwards, please see the figure on the right. We use the triangles formed by the rays, the object, and the camera axis to calculate distances using angle properties and trigonometry. Afterwards, we use all the angles and the distances to calculate the coordinate for object Pi. After we get the 3D coordinates for all objects, we regress a plane that fits the set of points the best. The optimization process minimizes the error in the angle estimation. The error here is a weighted sum of three terms. First is the perpendicularity constraint, where the object should be perpendicular to the ground. In other words, the object should be parallel to the normal vector of the plane. The second is the plane angle error, as the difference between the initial theta value used for the angle estimation process and the angle theta n obtained from the gradient of the plane. The last is the regression error, as the root mean squared error for the plane regression process. We iteratively do the angle estimation process until the error is smaller than a predefined threshold tau epsilon. Now for other details of CAMOT. For bounding box selection, we ignore bounding boxes on the frame edges, as this may harm the estimation process. Afterwards, to ensure that the bounding boxes have a balanced distribution, we horizontally divide the frame into several regions, then select one bounding box from each region. For angle initialization in the beginning of each frame's processing, we set from an initial value θ0 for the beginning frame, then afterwards we use the previous frame's angle θt-1. After we get the optimal angle, we perform angle smoothing to enforce the smooth angle assumption. We perform moving average on the angle with the window W to the past. So now we have the camera angles. We want to use them in tracking. So here we want to exploit a behavior in a bounding box distribution in the camera frame with respect to the camera angle. For low elevation angles, if you look at the images in the right, the objects are usually concentrated around the horizon. Usually, there are no vertical movement of objects within the image frame. However, for high elevation angles, the objects are more evenly distributed throughout the frame. So to exploit this, for the track association process, we wish to discourage vertical association on low angles. We do this by replacing the IOU with the modified distance IOU using camera angles. Next, we'd like to describe the experiments performed here. Here are our benchmark results on the MOT17 and MOT20 datasets. We improve on the others for most metrics on both datasets. We also perform experiments to measure inference speed, which proves that our method improves performance with only a slight decrease in speed. The ablation study here also proves that each component of our method contributes to the performance. In addition, we also try to use existing depth estimators in place of our bounding box depth estimation method. The results prove that our method remains competitive with the others while being much faster. Also, we try applying our method to existing MOT methods, which improve the performance of those methods. Now finally, we'd like to conclude this presentation. As a conclusion, this work introduces CAMOT, an angle estimator for MOT. CAMOT employs heuristics to adapt the tracking behavior to camera angles. CAMOT achieves state-of-the-art results and is computationally efficient. In addition, it is also applicable to other methods. For future work, we wish to use multiple frames in our process to improve stability. We also wish to explore applying CAMOT to general depth estimation problems. These are the references used in this presentation. So finally, thank you for watching this video and listening to my presentation, and we hope you have a nice day.